All right, folks. What we're going to be talking about today is the fundamental theorem of calculus, part 2. But first, before we get into that, what we're going to do first, first twice, now 3 times, is talk about the mean value theorem for integrals. Essentially, what the mean value theorem is if I am given a function, right? I'm given a function here where I'm talking about the integral from a to b of f of x. There is some value c such that if I choose that y value, let me do it in a darker color. What color should I choose? How about black? I haven't chosen black in forever. So there needs to be some value c, let's say it's right here, such that if I take f of c and I draw that horizontal line, the area, which it probably needs to be a little bit higher in this case. How can I move just that line? Let's just do this. The area of that value of c from a to b, that is not even close to a horizontal line. Come on, one more time, last time, I'm sorry. Last time to make a horizontal line. Whatever. So if I draw that horizontal line, the area underneath it, because I'm adding a little bit of area here to make up for that, the lost area right here and right here, and then there's a little bit of area added right there, such that the area all in here of the y value times the difference in the x values is equal to the area in pink there under my function f of x. So this gives me, the most important part of this is this really gives me the average value of a function. So given f of x on the interval from a to b, the average y value of that function is represented by this. Essentially all that I am doing, right, is I'm dividing over b minus a such that I have 1 over b minus a is equal to that, right, is equal to the y value such that it would be the average of the y values, because that would give me the same area under the curve. So this is how we can calculate the average value of any function, right? So it's changing. Average of a linear function is easy, right? It's just a plus b plus c divided by 3 or whatever, right? That's for usually a linear change, but not always. So what they will ask you is essentially just find the average value of each function on the interval. So you have to recognize that we are doing 1 over 4 minus 1, the integral from, oops, not equals. What are you doing, Mr. Bog? Not equals. Get out of here. The integral from 1 to 4 of x squared dx. And that will give me the average value of this thing. So this is equal to 1/3 times the integral of x cubed over 3 from 1 to 4. And then by my first fundamental theorem of calculus, I can do 1/3 times 4 cubed over 3 minus 1 cubed over 3. So that's what, 64? Yeah, 64 over 3 minus 1 is 1/3 of 63 over 3, which is equal to 21. 1/3 of 21 is 7. So the average value of that function is 7. So if I take the average of all of the points, right? So the instance where this is the average, there may be things in between here, but what we are able to do is this is actually taking the average of all of the y values, summing them up and dividing them by kind of infinity. But not really infinity, just by, it just breaks them down. I don't know, hopefully that makes sense, what that is doing. All right, so average value, 1 over pi minus 2 minus 0 times the antiderivative, so sine of x, from 0 to pi over 2. Just going to get rid of that bracket. So this is 2 over pi times sine of pi over 2 minus sine of 0 by the first fundamental theorem. So this is just 2 over pi times 1, so 2 over pi is my average value there. All right, so now we're going to get into the second fundamental theorem of calculus. Essentially, what is happening here is that if I take the derivative of an integral, notice this is from a to x of some function of a different variable, it is equal to putting x into for that other variable and then taking the derivative of the x if I need to. So let's examine this a little bit more. So I'm doing the derivative of the integral from a to x of f of t dt. So if I just look at the inside part here, then this would be equal to d over dx. So I'm going to leave the d over dx outside the same. Here, let me change that back to blue. Blue. Know how I did that, Natish? That's right. So this would be f, big F, right, from a to x by my first fundamental theorem, where big F, oops, sorry, that should be t. Big F is the antiderivative, right? Okay, that equals the derivative, I'm going to leave that alone, of big F of x minus big F of a. And a here is just a number. A is a constant. Number. That is just a number. So now, if I do the derivative of this stuff, check it out. If I do the derivative of f of x, well, that would just give me back to f of x, right? Because the antiderivative was big F. So if I do the derivative of the antiderivative, it's just back to little f. And then the derivative of number is 0. So I'm down to f of x, right? Right. By the chain rule, essentially if we had an x squared in here or something like that, then I would need to multiply this by 2x as well because I would have to do the chain rule inside. So that's why I have this derivative part off to the side. So we won't always have to think about it. So like this first instance, I'm not going to have to think about it because the derivative of x is just x. But literally, if I'm trying to find f prime, the derivative of f, then f prime is x squared minus 2x. Yay. That's it. Sweet. All right. Now here in this case, I have an x squared. So if I want to do the derivative, then I need to put in x squared and then multiply that by the chain rule by 2x. And that would be it. You could simplify this stuff if you want to as far as distribute everything out. So let's see, that would be x to the 4th minus 2x squared times 2x. So this would be 2x to the 5th minus 2x to the 3rd. Cool. All right, so now this is a little bit different because this is in the denominator. So going back to our initial kind of setup, my first part was when I had x up top. Well, now if I have x in this spot, that means there will be an x in this spot, which means it was negative. So when I do this, all I'm going to do is make this the negative of it. So f prime would be negative 6x squared. The other thing that you can do is the integral from 1 to 2 of dx is the same thing as the negative integral if I flip it. Right, that was kind of one of the characteristics that we talked about. If we flip the numbers, it just makes it the negative integral. So you could also rewrite this as negative the integral from 5 to x of 6t squared dt. And then it's easier to see where the negative is coming from as well, right? Because then I'm just going to throw the x in for t, and it's 6x squared. All right, part D down here. So if I do the derivative, then f prime is, I'm just going to go ahead and multiply by the derivative of sine, so cosine, and then times, throw your sine into the t spot, so sine of x, sine squared of x, right? Right. All right, Give me just 1 second and I will get into this problem. Hang on. Okay, take a minute, check out the example, and then we're just going to go through these. These are going to be a very good type of question that you could see on the AP test. Yeah, so let's just get after it. Notice it says let g be the integral of this function. This is f of t here. I should have labeled it for you, but that is f of t right there on that graph. Okay, so find g of 0. Well, g of 0 would be when I do the integral from 0 to 0 of f of t dt, which would just be 0 because it's going from the same x value to the same x value. So there's no area under that curve. All right, and then g of 4 will be the integral from 0 to 4 of g of t dt, which from 0 to 4, so let's think here right now, there and there. Let me draw in a different color so you can see it a little bit better. There and there, that is a triangle, right? Where the base times height is 4, the base is 2, the height is 2. So 4 divided by 2 is 2, so that area is 2 units. Then I have a square here, so 2 times 2 is just 4. I have another triangle next. Base times height would be 1 times 2, divided by 2 is 1. And then I have kind of 2 triangles down here with an area of -1 each. So the area altogether down there should be -2. Okay, so now let's go think about from 0 to 4. All right, so from 0 to 4, I'm adding up those areas, which would be 6. And then g of 7 would be the sum of all of the areas. So I have from here to here, that total 7, and then -2 would total 5. Find the interval on which g is increasing or decreasing. So for g to be increasing, I want to know when g prime is equal to 0. So let's think about what g prime is. G prime is equal to the derivative from 0 to x of f of t dt. So it would just be putting in f of x. So f of x is going to be 0. Let's see, at 0, but we're not going to really include that, right? So g prime equals 0 when x equals 0, 5, and 7. So if I'm thinking about my areas, I am positive. Let me make sure I explain this right. Yeah, okay. So important relationship to recognize is that this graph is also g prime. So my outputs here, this is essentially the graph of my derivative of g, because f was the integral of that. So if I take the derivative of g, that just gives me f, which is what we saw, right? So if I'm thinking about this on a number line, I'm increasing when my derivative is positive. So I'm increasing on the interval from 0 to 5 because g prime is greater than 0. I am decreasing on the interval from 5 to 7 because g prime is less than 0. Cool. All right, finding any extrema. Let's see, x equals 0, but am I given any initial? Not. I should have given you something. G of, no, I'm lying. It's okay. Yeah, because f, g of 0 is 0. Yeah, okay, sorry. So I need to check g of 0, which is 0. I need to check g of 5, which is 7. I need to check g of 7, which is 5. So I have a min, relative min, because that's an endpoint. I should have given you all more room, I'm sorry. I have a relative and absolute max. Because G prime goes positive to negative. And then I have a relative min, really just because it's an endpoint. I'm decreasing until the endpoint. Okay, any intervals on which G is concave up or down? So really G prime needs to be increasing or decreasing at those points. So I'm concave up from 0 to 2. So 0 to 2 and 6 to 7 because G prime is increasing, and concave down on 4 to 6 because G prime is decreasing. All right. So just making that relationship to that f is the derivative of g is also super useful in this stuff. Kind of when we do that, that makes things move a lot more smoothly through giving our answers. But other than this stuff, that's really it. Let me know what questions you have as you are going through your homework, and I will talk to you all soon. Bye.